looked at a poll, maybe something about voting intentions or, consumer habits, and just thought, how did they figure that out?
Yeah, like how do they know what everyone thinks just by asking maybe 1,000 people?
Exactly. It seems like they're trying to understand this massive group by talking to just a tiny fraction.
And they are, but there's a real method to the madness. It's all about how you choose that small group to make sure it actually reflects the big one.
That's what we're diving into today, sampling design.
And we're using some really helpful lecture notes as our guide from Jae Choi at George Washington University.
Right. Think of this as sort of your inside look at how researchers get their data. Our mission to unpack the main ideas, look at the different ways they select people, and how they land on that number, how many people are enough.
It really gets to the heart of whether you can trust the findings, doesn't it?
It really does. So let's start with the fundamentals, the population and the sample.
Okay, so the population. That's everyone or everything you're interested in studying. Could be all the students at a university, like you said, or maybe all the cars produced by a factory.
The whole group.
The whole group. And the sample, that's the smaller slice you actually look at, the ones you collect data from.
Makes sense. And the aim is usually to say something about the whole population based on that smaller sample.
Precisely. You want to generalize. And the key technique, often the ideal one anyway, for bridging that gap is randomization.
Randomness.
Yeah, but used in a couple of distinct ways. First up is random sampling. Sometimes people say random selection.
And that's about how you pick the sample.
Exactly. How you choose individuals from the population to be in your study. The core idea is giving everyone in that population a known chance, usually an equal chance, of being picked.
Why is that so important, giving everyone an equal shot?
Well, it's your best bet for getting a sample that truly represents the population in all its variety. This ties directly to generalizability, or what researchers call external validity.
So how well your findings apply beyond just the people you talk to?
Right. If you randomly sampled students from the entire university, your findings are more likely to apply to all students than if you, say, only surveyed people in the library cafe.
Okay, yeah, that's clear. But trying to randomly pick from, all eligible voters in the U.S., that sounds incredibly hard.
Oh, it is. It really is. One of the biggest practical roadblocks the notes mention for true random sampling, especially with big populations, is just getting that complete, accurate list of everyone. The sampling frame, they call it.
The master list.
Yeah. Imagine trying to list every single adult resident. It's, well, practically impossible in many cases.
Okay, so random sampling is about who gets selected for the study. What was the other kind of randomization?
That's random assignment. This comes after you've got your sample.
Right.
If you're doing an experiment, like testing a new drug or teaching method, you take the people in your sample and then randomly assign them to different groups.
Like one group gets the new drug, the other gets a placebo.
Exactly. Or one class uses the new method, the other uses the standard one.
So sampling is picking the players. Assignment is dividing them into teams for the experiment.
Perfect analogy. And random assignment is absolutely crucial for what's called internal validity. It helps ensure the groups are basically equivalent before the experiment starts.
So any difference you see later.
You can be much more confident it was caused by the drug or the teaching method, and not just because the groups were different to begin with. It's key for making causal claims.
Got it. Now, even if researchers do everything right with randomization, sampling isn't perfect. There's still variability.
Yeah, absolutely. The notes talk about a couple of key concepts here. First is sampling variation.
Okay.
This is just the natural expected difference you'd see between different random samples drawn from the same population. It's pure chance.
Like if we both randomly sampled 100 people from the same city about their favorite pizza topping, we wouldn't get the exact same percentages for pepperoni.
Probably not, no. Those small differences, just due to the luck of the draw, which specific individuals happen to end up in your sample versus mine, that's sampling variation, it's normal.
And the notes say this variation gets smaller with bigger samples.
That's right. The bigger the sample, the less variation you expect from sample to sample. If you sampled the entire population a census, there'd be zero sampling variation because there's only one possible result.
Okay. Then there's sampling error. How's that different?
Sampling error is about how much your one sample's result, say the average income in your sample, differs from the true average income in the entire population.
Ah, so it's sample versus the population value, not sample versus another sample.
Exactly. It's the unavoidable discrepancy because your sample is only a part, not the whole. We usually don't know the true population value, but we use statistics to estimate the margin of error around our sample finding.
So variation and error are kind of expected noise due to using a sample.
You could put it that way. They arise from random chance in the selection process. But then there's the one we really try to avoid: sampling bias.
Right. You mentioned this is the bad one.
It is, because unlike variation or error, bias isn't random, it's a systematic problem. It means your method of choosing the sample consistently favored certain types of people or responses over others.
So the sample is skewed from the start, not just by chance.
Precisely. The example in the nose is great. Collecting data only outside the main university library between 11 a.m. and 3 p.m.
Yeah, you mentioned that. You miss whole groups of students.
Right. Evening students, commuters, maybe grad students based elsewhere, people working jobs during those hours. Your sample wouldn't represent all students. It would be systematically biased towards those who are near the library midday.
And that bias messes up your ability to generalize findings back to the whole student body.
Totally. You can estimate and account for random sampling error statistically, but bias, that undermines the whole representativeness goal. It's a flaw in the design itself.
Okay, so minimizing bias is crucial. What's considered the best way to do that, the sort of gold standard method, when it's actually possible?
That would be simple random sampling, or SRS.
Simple random sampling?
Yeah.
Sounds simple.
Conceptually, it is. The definition is straightforward. Every single person or unit in the population has the exact same probability of being selected.
Equal chance for everyone.
Equal chance. If you can achieve that, your sample is, by definition, unbiased. Any deviation from the population is just down to that random sampling variation we talked about.
And how do you actually do it? Assuming you can overcome that hurdle of getting the list.
Right, assuming the list exists. Step 1, get the complete list, the sampling frame. Step 2, decide your sample size and calculate the sampling fraction. Say you want 400 students out of 4,000 total. Your fraction is 110.
Okay.
Step 3, use a randomization tool. This could be random number tables, software like SPSS, or even websites like randomizer.org to pick units from the list purely at random until you reach your target size.
So SRS is the ideal for generalizability because it eliminates selection bias. But that big if is getting the list.
That's often the Achilles heel, especially for large populations. It's theoretically pure, but practically challenging.
Which leads us to why researchers often have to use other methods, right? When SRS just isn't feasible.
Exactly. The notes say researchers depart from SRS when that list is unavailable, or the population is huge and dispersed. Or, importantly, when the population isn't uniform. Meaning it's very diverse with distinct subpopulations or strata, or when it's naturally arranged in groups or clusters.
Like students in different schools or people living in different neighborhoods.
Yes, exactly. Schools, districts, states, hospitals, workplaces. These are natural clusters. The U.S. population itself can be seen as clustered by state, then county, then city, and so on. Working with these existing structures can be much more practical.
And when things get complex like this, choosing a sampling method involves juggling different priorities.
Absolutely. The notes highlight 4 key criteria. Goal orientation. Who exactly do you want to generalize to? Measurability. Can you actually get the data you need from the people selected this way? Practicality. Is it even doable with your time and resources? And economy. What's the cost?
So it's a balancing act.
Always. Balancing the ideal scientific rigor against real-world constraints.
Okay, let's talk about some of these complex methods. How about stratified sampling?
Right. Stratified sampling is really useful when your population has known subgroups, or strata, that you want to make sure are represented. Think different departments in a company or racial groups in a city.
So you know these groups exist and are important.
Yes. The steps are: 1, divide the whole population into these non-overlapping strata. 2, draw a separate random sample from within each stratum.
Ah, so you sample from every group.
Correct. You can take an equal number from each stratum, or more commonly, you take a number proportional to that stratum's size in the overall population.
Like your university example earlier, if 60% are humanities majors and 40% science, a proportional stratified sample of 100 would randomly pick 60 humanities students and 40 science students.
Precisely. The source example involves taking a 10% sample from each academic major. The big advantage is that it guarantees representation for all your key subgroups. No group gets missed by chance, and you often get more precise estimates for each subgroup.
Can you stratify on more than one thing? Like major and year in school?
You can, technically, major and undergrad status, for instance, but it gets complicated fast because you end up with many small strata. The notes suggest usually sticking to one or maybe two stratifying variables, keeping the total number of strata manageable, maybe under 20.
Okay, what about cluster sampling then? How's that different?
Cluster sampling works when the population is naturally grouped into clusters, like those schools or neighborhoods we mentioned.
Right.
The steps here are: 1, define your clusters; 2, randomly select some of the clusters; 3, collect data from everyone inside the selected clusters.
Whoa, everyone.
Everyone within the chosen clusters. So, stratified samples from all groups, cluster samples, all people in some randomly chosen groups.
That seems different, less spread out.
It often is. You're sampling groups, not individuals scattered across the whole population. One implication is that your final sample size might not be precisely known beforehand unless all clusters happen to be the exact same size, which is unlikely.
Like picking states, California is way bigger than Rhode Island.
Exactly. The notes also mention that cluster sampling can sometimes be less statistically efficient, meaning you might need a larger total sample size to get the same level of precision as SRS, or stratified sampling. This is often because people within a cluster, like a neighborhood or a school, tend to be more similar to each other than people randomly drawn from the whole population.
And you can do this in stages too.
Mm.
Multi-stage cluster sampling.
Yes, very common for large geographic surveys. You might randomly select states, stage 1, then randomly select counties within those states, stage 2, then maybe towns within those counties, stage 3, and perhaps households within those towns, stage 4.
Wow, okay. Layer in the clusters.
Yeah, at each stage, you're narrowing down based on random selection of clusters driven by practicality. Interestingly, the very last stage might involve randomly sampling individuals within the final chosen cluster, like sampling students within a selected school, which starts to look a bit like stratified sampling at that final step, even if the overall structure is multi-stage cluster.
Okay, one more complex type mentioned. Systematic sampling.
Ah, yes. This one can be very convenient if you have your population ordered in some way on a list.
How does it work?
You first calculate your sampling interval, K. If you want a sample of 100 from a list of 1,000, K is 10, 1,000, 100. Then you randomly pick a starting number between 1 and K, so 1 and 10. Let's say you pick 7. You select the 7th person, then the 17th, the 27th, 37th, and so on, every 10th person from your random start.
That does sound efficient. Just count down the list. What's the catch?
The big danger is something called periodicity. It's a risk if there's some hidden pattern or cycle in the order of your list, and your sampling interval K accidentally lines up with that pattern.
How so?
Well, the notes use an example. Imagine a list of students ordered by GPA, maybe highest to lowest repeating in cycles for different programs. If your K happens to always land on, say, students just below a certain cutoff, and you're studying something related to academic achievement, your sample could be seriously biased.
If the list order isn't random with respect to what you're measuring.
Exactly. If the list order is effectively random, like alphabetical by last name, and last name isn't related to what you're studying, then systematic sampling can work almost as well as simple random sampling and be much easier. But you have to be careful about that potential periodicity issue.
Right. Okay, so we've covered how to sample in different ways, but the massive question is always, how many? How do researchers figure out the right sample size?
Yeah, that's a critical decision. It's not just plucked out of thin air. Several factors weigh in. A major one is statistical power and precision.
Power and precision. Tell me more.
Okay, power is the ability of your study to detect a real effect or difference if one actually exists in the population. A small sample might miss a real but subtle effect. Precision is about how narrow the margin of error is around your estimate. Larger samples generally give you more power and more precision. Your results are more likely to be statistically significant if there's a real effect, and your estimates are likely closer to the true population value.
So bigger samples give you more reliable statistical conclusions.
Generally, yes. The notes link this to statistical conclusion validity. Small samples make your statistical tests less robust, more sensitive to assumptions being slightly off.
Makes sense. What else influences the size?
Effect size. This is about how big of a difference or relationship you're actually expecting to find. Are you looking for a massive impact or a tiny nudge?
And how do you know that beforehand?
Good question. Ideally, you look at prior research. What effects did similar studies find? You estimate the likely effect size based on the literature. Knowing the effect size you're looking for and the level of power you want, often 80%, lets you mathematically calculate the needed sample size.
That calculation has a name.
Yes, it's called a priori sample size determination, or
Yeah.
sometimes just power analysis.
So if you're hunting for a really small effect, you'll
Mhm.
need a bigger sample size calculated through that power analysis.
Exactly. To reliably detect a faint signal, you need a bigger net. And then, of course, there's the inescapable factor of cost.
Right. Time and money.
Recruiting participants, collecting data, analyzing it, it all costs resources. So you have to balance the statistically desirable size with what's practically affordable and feasible.
Now, you hinted earlier, and the notes point this out too, that just saying more is always better for sample size isn't quite right.
It's a really crucial point, especially now with big data. Yes, larger samples increase power and precision, but there are diminishing returns. Doubling your sample size doesn't necessarily double your precision. Also, more complex statistical models, ones with lots of variables, generally do need larger samples to be stable.
But what's the potential downside of a sample being too big?
This is the idea of an overly powerful scenario. With a massive sample size, your study might have so much power that even incredibly tiny, trivial differences that have absolutely no practical meaning in the real world become statistically significant.
Meaning the math says it's unlikely due to chance, but the effect itself is minuscule.
Precisely. Like finding a new fertilizer increases crop yield by, 0.01%. And because you tested it on a million plots, it's statistically significant. But that 0.01% is practically useless.
So statistical significance doesn't automatically equal real-world importance.
Not at all, especially with huge samples. An overly powerful study can make it hard to see the forest for the trees. You get lots of statistically significant results, but only some might actually matter.
So summing up on sample size, it's a balancing act.
It really is. You use things like a priori sample size determination to figure out the minimum needed for decent statistical power and valid conclusions, especially if your analysis is complex. But you also need to consider if a massive sample might just be wasteful or lead you to focus on trivial findings.
So you need to justify why it's big enough, but perhaps also why it's not too big.
Exactly. It's about finding that sweet spot, an appropriate range.
Wow. We've really gone through the whole process in this deep dive, guided by Professor Choi's notes, from population versus sample to the roles of random selection and random assignment.
Yeah, and navigating those different kinds of variation, the expected random variation and error versus the systematic bias we want to stamp out.
Then exploring the different tools. Simple random sampling is the ideal, but then the practical adaptations like stratified, cluster, and systematic sampling for more complex situations.
And finally, tackling that crucial question of how many, balancing statistical power, effect size, cost, and even the risk of having too much power.
It really underscores how much thought has to go into this stage. The sampling choices fundamentally shape what you can actually claim from your research.
It does, and it leaves you with a bit of a practical dilemma, doesn't it? Often the most convenient or cheapest methods, maybe cluster or systematic sampling, might not give you quite the same level of pure representativeness as a painstakingly constructed, simple, random, or stratified sample.
Right.
So does the real-world need for efficiency or affordability ever justify using a method that might be slightly less scientifically? How do researchers balance that practical pressure against the absolute pursuit of the most representative sample possible? It's a constant tension.